Managing Complexity, Part 3. This part of the video is about recursion. Actually, by now, you should already be very familiar with recursion, ever since you used picture language in Lecture 2. Recursion. Recursion is a special case of a wishful thinking. The original problem is broken down into smaller child problems that each has the same structure as the original problem. Now, you may scratch your head then. Does this mean that we don't really solve a problem? We simply push it down to someone else? No, as you will see, you must eventually solve the smallest problem or problems to complete the solution. As mentioned, we have seen this before in Lecture 2. This picture is from our homework. It seems to be repeating in many levels. So if you take this as n levels, then we would have one at the n-1 levels. In fact, we have another one below it that is also at n-1 level. So this whole picture could be viewed as a cross next to two pictures of itself at the lower level, one on top of the other. At the lowest level, which is the base case, we simply have a cross next to two crosses, one on top of the other. Here is another example from the previous video on taxi fare. You have defined taxi fare. For the distance at beyond 10 km, you have actually called taxi fare recursively. Again, there should be base cases. For this problem, the two base cases are when the distance is less than or equal to 1 km and the distance is less than or equal to 10 km. So when the distance is less than or equal to 10 km, you simply return the value calculated from here or from here. Now we see the standard example of recursion, factorial function. N factorial is equal to n times n-1 times n-2 all the way until 1. So if you rewrite this into a recursion, this is n factorial is just 1 if n is 1. Otherwise, it is equal to take out the n times n-1 factorial if n larger than 1. So this is the definition. And let's see the Python code for factorial. Define factorial n. If n is equal to 1, just return 1. Otherwise, return n times factorial of n-1. So this is directly translated from this definition of factorial. Let's take a look at it again. Factorial. There's this part of a simple calculation, and there's this part of recursively calling itself. This part of the simple calculation is terminating condition. That is, when the problem gets down to n equal to 1, you will just simply return 1 without any more function call. And this is also called the base case. If not, there will be a recursive call with a number smaller than the original input by 1. So a function that calls itself is called a recursive function. Now let's look at the whole process of recursion. When the input to the factorial function is n, we can't have the answer. We need the answer from n-1 to get the answer for n. And for n-1, again, we need the answer from n-2 to get the answer, and so on, until 2, and then 1. At 1, this is a trivial case. We hit the terminating conditions. The answer is trivial. It is equal to 1. And from this answer, we can then pass it back to factorial 2 to get the answer for factorial 2, and so on until n-2 and n-1, and then finally n. Here is one more look at the process with a specific example of factorial 6. So to calculate factorial 6, we have to find factorial 5. And so 6 times factorial 5. And to find factorial 5, we need to get from factorial 4, and so on until factorial 1. This is the base case, and we know the answer, which is 1, and therefore we have the 1. So the 1 will now be returned and be multiplied with 2 to get 2. 2 is then returned to multiply with 3 to get 6, and so on, until we have the answer for factorial 6, which is 720. Note that the front part of this whole process has a build-up of the multiplication. They are not done until much later. For this guy, it is done only after factorial 1 returns a 1. And then for this guy, it is done after 2 is returned, and so on. We care about such panning operation because we care about the time and space of a program that we next take a closer look. We don't just write program to solve a problem, but we also need to know how good our solution is. To analyze our solution, we are always interested in the time and the space. The time means how long it takes to run the program, and the space is how much computer memory do we need to be able to solve the problem. This is in the subject of time and space complexity. Let's analyze the factorial function. Time is needed to do arithmetic operations. So the time needed is proportional to the number of operations we do. So for factorial with input of 6, we need to call factorial 5, factorial 4, factorial 3, factorial 2, and factorial 1, all 5 times. And also we need to do multiplication 1 time, 2 times, 3 times, 4 times, and 5 times to arrive at the answer 720. This is for factorial 6. So likewise, for factorial n, we need to call factorial n-1 times and do multiplication n-1 times. So the number of operations is linearly proportional to n, and so the time is also linearly proportional to n. What about space then? We see that we need space to keep track of panning operations. So the space requirement is proportional to the number of panning operations we have. So here, for factorial 6, the panning operation includes factorial 5 yet to be completed, factorial 4, factorial 3, factorial 2, and factorial 1. Also, we need to eventually calculate the multiplications here. So there are 5 of them. So in general, factorial n will require to have space to keep track of n-1 factorial calculations, as well as n-1 multiplication yet to be completed. So the number of panning operation is linearly proportional to n, and thus the space requirement is also linearly proportional to n. To recap, to come up with a recursive solutions, we need the base case or base cases. Typically, we have n equal to 0 or n equal to 1. Then we assume we know how to solve the problem for n-1 or even smaller cases. We then use this information to solve the problem for n. Let's see another typical example in recursion. Fibonacci numbers. This is named after the person who came up with the sequence. The first two numbers, 0, 1, are fixed, and then subsequent number, next one, it's the sum of the previous two. So 1 is equal to 0 plus 1. And likewise, 2 is equal to 1 plus 1. Then 3 is 2 plus 1, and then 5 is 3 plus 2, and so on. So to write it in a recursive manner, we have Fn, Fibonacci numbers, is equal to 0 when n is 0, is equal to 1 when n is 1. Otherwise, it's equal to the sum of the previous two Fibonacci numbers. So this is straightforward to convert to Python. We have define Fibonacci n colon when n is equal to 0, when n is equal to 0, you simply return 0. When n is equal to 1, you simply return 1. Otherwise, you return the Fibonacci number of the previous one plus Fibonacci number of the previous one. Let's see how this recursion works. Phi5 will call Phi4 and Phi3. Phi4 will call Phi3, Phi2, and likewise Phi3 will be Phi2, Phi1, and so on. Same here, Phi2 will be Phi1, Phi0, and Phi3 will be Phi2, Phi1, etc. This is a tree structure in computer science, where you have branches and going downward, and there's no looping. This is called the root. Those with no outgoing branches are the leaves of the tree. The rest of them, like Phi1, Phi0, those tagged with the Phi, are the non-leaves, and they are called the internal nodes. From this tree, we can study the time needed for this recursion. The time needed for this recursion is the number of branches you see in this picture. So it is the number of leaves plus number of internal nodes. In fact, the number of internal nodes here is about 2 times the number of leaves. So the time for this recursion is proportional to the number of leaves. What's the number of leaves then? The number of leaves in this case is actually Fibonacci n plus 1, which can be proven with mathematical induction. And Fibonacci number n is actually phi to the power of n divided by square root 5. where phi is actually 1 plus square root 5 divided by 2, and it is called the golden ratio. So the time taken is proportional to phi to the n, which is 1.618 to the n. So this is exponential in n. Next, what about the space then? The space required is actually proportional to the depth of the tree. That is linear in n. Why is that so? Let's take a look. Fibonacci 5 actually call Fibonacci 4 first before it enter into Fibonacci 3. And 4 actually enter into Fibonacci 3, then Fibonacci 3 into 2, and then into 1 to get the result of 1, then back up to get to Fibonacci 0 to get the result, and then back up, and so on. Then this is 8 and 9 and 10, and then 11, 12, 13, 14, 15. Now, along the way, when it goes into this manner, alright, the moment that you need to back up from Fibonacci 1 back to Fibonacci 2 into Fibonacci 0, it can actually reuse the space by 5 here for 6 and so on. So at any moment in time, the deepest that it can go is the depth of the tree, and this is the amount of space that you need to have to complete the whole calculation. Now you know the space can be reused, but time cannot be reused. Once the time is used up, it is gone. But the space you need could be referring to some old space, like here. The 6 is using the space of 5. So it is good to note that the space complexity, the amount of space that you need, can never be larger than the time complexity, the time that you need, in all applications. In our various examples, you actually see different kinds of recursion. We shall give them names. The easiest is the linear recursions, where we saw factorial is called by factorial only once. It looks like this in the recursion, and this is called the linear recursion, as it makes a single call to itself each time the function runs. In the Fibonacci number, we actually call Fibonacci twice in the function, and it resulted in this exponential number of calls, and this is the exponential recursion. This is yet another kind of recursion, where ping call pong and pong call ping in turns. So the output for this case with ping 10 is ping pong ping pong ping pong ping pong ping pong 10 times. So a recursion does not necessarily call itself only. This type of recursion is called mutual recursion, and they work in pairs or even larger groups. To sum up this part of the video, we have talked about recursion solutions. In the solution, you should have two parts, the base cases and solution of the original problem from solutions of smaller problems. Recursion is a form of wishful thinking, where the smaller problems has the same structure as the original problem. In the next video, we'll see more about recursion solutions in comparison to iteration solutions.